Hey, Algebra 2 friends, here we are at the end of Chapter 10. We're going to be talking about exponential growth and decay. So our vocabulary consists of two phrases, rate of decay and rate of growth. And they're kind of self-explanatory, but I think it probably could use a little bit extra explanation. So, things can decay at a particular rate, usually given in the form of a percentage or a fractional amount of how much of a particular substance will be lost over time, or how much the value of something depreciates over time. Typically, you know what the exponential equation is going to look like. An exponential is in its rarest form, or most general form, I should say, is y is equal to a times b to the x power. When we talk about exponential decay, this a value is the original amount, so it's going to be y is equal to the original amount, or your starting amount, times um, 1 minus the rate of decay. And we'll talk about that in a second. So your B value will be 1 minus the rate of the decay, the rate of loss. So if you're thinking about buying a car, and if you were to purchase a car and then somebody usually makes the comment that, once you drive it off the lot, the depreciation starts immediately. And let's say that depreciation is the value depreciates by 12% a year. That means for every year, the part of the 12%, I'm going to do this, the part that remains, the part of the value that you maintain is only 88%. So in this case, this would be the amount you paid for the car, and this would be the number of years you own the car up here. Generally, we use T, which would make better sense. And so this is what a rate of decay equation would look like, and the rate of decay is usually we usually use 1 minus that rate of decay to complete our exponential function. All right, so with that, let me go ahead and get another color pen so you can keep track of my thought process. And rate of growth, so if we're growing by 10% a year or 5% a year, whether it's financially or the colony of bacteria, again, we start off with y equals a to the bx power, where x turns into t again. B is an increasing value, and a is the amount you start off with. So it will be 1 plus the rate to the t power. So for instance, if I start off with some money in the bank account, and that will be A, and I'm telling you that the money is going to increase 10% per year, that means every year I'll have 1.1 times the original amount that I had. If you think about that, that'll make sense. But if it increases 10% every year, this 0.1 represents the percentage of 10%, right? If it increases every year at that rate, then I'd raise it to the t power. This is different than continuously compounding. And again, that's something we'll talk about in person. It'll make good sense. All right, so rate of decay is the percentage at which something decays, and we usually write it like this. And the rate of growth would be the percentage at which something grows. In this case, my example was 10%. Let's go on and try some examples. So here in example 1, we are expected to consider a cup of coffee that contains 130 milligrams of caffeine. If the caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for half of this caffeine to be eliminated from a person's body? Okay, so let's think about all the information we are given. So with a little thought, here are some things that I think are important. Original amount of caffeine, which is usually a great place to start. So we have 130 milligrams of caffeine. Rate of decrease. So the decrease is 11%. Sometimes we might even include a negative to emphasize its decreasingness. And for me, I'm putting this down. This isn't really a thing that you're going to calculate, but you need to be specific about it. The decrease is per hour. So the unit of time is hour. So this T, sometimes it could be years, sometimes it could be days. This T refers to hour. So here's our equation that we're going to start off with. We know y is equal to a, which is 130, times 1 minus 11, right? Or 1 plus the negative 11 if you want to look at it that way. And that will be written as 11 the percentage will be written as a decimal, and then we'll raise it to the t power. That's what we're looking for. So we're looking for time when what will happen. So this is a great starting place, but now we need to be a little bit more specific. We want to know when there's half of this caffeine is eliminated. So if half of the caffeine is eliminated, starting with 130, we only have 65 milligrams of caffeine left. So we are now getting into where our equation should be. So this is 0.89. And this is to the t power. So this is our equation that we're going to use to solve. And I think from here, the setup is probably the hardest thing. You all are pretty strong and you know how to solve this. We're going to divide both sides by 130. And we know that this is just 1/2 is equal to 0.89 to the t power. In order to solve, what we'll do is to get an exponent that is a variable out of the exponential place so we can kind of handle it, we take the log of both sides. Natural log, common log. Let's do common log for old times because we haven't done it in a lesson or so. So I can do the common log of 1/2. I'm just going to do log of both sides is equal to the common log of this side over here. And so if I take the common log of this side, I can write t as a coefficient. So it's really t times the common log of 0.89 is equal to the common log of 1/2. All of these are very calculatable values. So I'm going to finish this off by dividing both sides by the log of 0.89. So then let me draw an arrow over here. So then what happens is I get that t, follow me now, is equal to log of 1/2. I'll put 0.5 just to make it look like a normal non-complicated fraction, divided by the common log of 0.89. And this is going to take calculator work. You're going to plug it into your calculator and you'll get something like this, approximately 5.9480, or approximately 6 hours, about 6 hours it takes for that caffeine to decrease by half. And so it makes sense when people tell you not to drink caffeine right before you go to bed because it takes a while to dissipate out of your system. All right, so we're looking for exponential decay in this form. So this form of exponential decay is going to be more useful when you take your science classes. I will personally tell you that this would not be my natural way of solving this problem. I will probably do a half-life formula, and I can show you that in class if you'd like. But we should feel comfortable using this. So here is an exponential decay form, particularly in science classes, where we have this constant K that is specific to the situation. So in this case, we're dealing with the half-life of radioactive substance is the time it takes for half of the atoms of the substance to become disintegrated. All life on Earth contains the radioactive element carbon-14, which decays continuously at a fixed rate. So this is how, by the way, they kind of can age different things and say how long it's been on the Earth, how scientists use carbon-14 to do so. So the half-life of carbon-14 is 5,760 years. That is every 5,760 years, half of the mass of the carbon-14 decays away. So what is the value of K for carbon-14? So we start off with Y is equal to A times e to the negative kt power, where the time that we're talking about is, well, here's what we're thinking. If we had 1/2 of the original amount, 1, it would be e to the negative k, but it would take 5,760 years. What am I doing? I'm saying if I had one batch of carbon-14 and I wanted to figure out how long it would take to reach half of that amount, I know that that amount of time would be 5,760 years. So I put that in T. T in this problem is referring to years. And now I can solve for the K value for this particular substance. And as you can see, every substance with a different half-life will have a different K value. So we'll do this by taking the log of both sides. Natural log of both sides will work here very well. Taking the natural log of both sides leads me pretty much immediately to the realization that negative K times 5,760 is equal to the natural log of 1/2. We remember the canceling out property there. I'm going to have to divide both sides by 5,760 760, and let's do the negative version of that. And when I do that, again, a little bit of calculator moves will yield that k is equal to this really, really tiny number, 0.00012. All right, so now we can use that information to solve this last part of the problem. A paleontologist examines the bones of a woolly mammoth, estimated that they contain only 3% as much carbon-14 as they would have contained when the animal was alive. How long ago did the mammoth die? So if I'm taking that original function, that original relationship, I'm plugging in the K constant that we have for carbon-14 because that is the radioactive substance that we're using. Now I need to put in 3% versus the original amount. And if I wanted to calculate that, 3% of A, of this original amount, would be 0.03. A is equal to A times e to the negative 0.00012t. And so really it feels like we have a lot of variables left, but we only have one. Okay, e is not a variable, which sometimes it feels like. If we divide a out of both sides, that's going to just leave us with 0.03 is equal to e to this particular power, where t is the only variable. So now we need to solve for t. You know what we'll do. We'll take the natural log of both sides, and we end up getting that the natural log of 3 is equal to that exponential value. And so now things are a little bit easier. We'll divide both sides in order to isolate that t value. And then with a little bit of calculator work, we get that t is equal to approximately 29,221 years. Okay, so in this example, we're looking at this form of the growth equation. And so what we have is a population of original amount being 120,000 people. And we know that the city grows at a rate of about 1.5% per year. When I write that as a percentage, it is 0.015. So I'm adding 0.015 to the 1, right? Because this is an increased situation, and t is the number of years. Well, if we're starting in 1910 and we're going to 2010, that's going to be 100 years. So with calculator work, we can answer this question. And we get 531,845, and we can see that B is the answer. Our final problem is looking at the relationship or the comparison of the populations of China and India. So as of 2000, China was the world's most populous country with an estimated population of 1.26 billion people. The second most populous country was India with 1.01 billion. The populations of India and China can be modeled with these equations. So they gave us nice equations with the K values already there. Yay! Respectively, according to these models, when will India's population be more than China's? We create the inequality where we're considering what time it will be when India's population is greater than China's. So we write it this way. What we'll do now is we'll take the natural log of both sides. And what that'll do, it'll give us the opportunity to get this exponent out of exponential place and so kind of get the t out of the exponent so we can deal with it. But first we have to realize that we are taking the natural log of a product. Using our log laws, we know that that means that we're taking the natural log of two things that we're finding the sum of. So we'll rewrite it like this. So once we get this expression, we can now eliminate the e values here because that's what the natural log does. And our inequality now looks like this because we got to eliminate the e values. So that's great. Now we get to move all the t values to one side, all the constants to the other side. Believe it or not, the natural log of 1.01 is a constant. When that happens, this inequality here, right? And then we can join our like terms and we have this final relationship that we're going to just divide both sides by 0.006. And I like to leave all of my calculator work for the end so I can get my t value. So t has to be greater than, according to my calculator, 36.86 years. So in 37 years, we expect the population of India to be greater than the population of China. Well, 36 years from 2000, so 2036. All right, my friends, I'm out.